Continuing our discussion on process scheduling, we are now going to look at something called real-time scheduling. So all the scheduling scenarios we saw so far, your first come first served, shortest job, shortest remaining time, preemptive, non-preemptive, priority, round robin, multi-level queue, feedback queue, all of that, you had a bunch of tasks given to you. You had some the burst time. In some cases a priority was given, in some cases an arrival time was given, whatever. So we worked with the assumption that this process needs this many units of time to complete, which is specified by its burst time. So if it starts at this time and you allow it to run for this many cycles, it is done. That's all. We are finished with the process. It terminates. That is not necessarily how all processes in a real-time system might work. Okay, so there might be some processes which happen recurrently, as in every few units of time this process needs to keep repeating itself. For example, your system updates, your antivirus checks are an example of processes which need to be repeated once in a few months or few weeks or whatever, right? So a system update is not a one-time thing. You update it once and it's done. You don't have an update ever after throughout the lifetime of your device. That's not how it works. Every month or 2 months, 3 months, 6 months, whatever, new updates are offered and you get that notification. You have to update your system. Same thing with your antivirus. If you have an antivirus software installed in your PC, there is a time period for which it runs, and when it's expired it needs to be reinstalled or renewed or whatever. So there are processes which happen recurrently. So these, which I just gave you an example of, the time period is usually like months or at least weeks. There could be processes which happen every few minutes or seconds or hours also. So my bottom line here is there are processes which are not a one-time thing, but they keep repeating in a periodic fashion. That is one thing. Also, you might have processes which have deadlines. That is also something which you might come across in your system. So in our examples we only saw burst time, which means this process needs these many units of time to be completed. But some processes could also have deadlines, like if this process is not completed within this time, then there's no meaning. That kind of scenario can also be there. So those are some things which you encounter in real time, which our previously discussed algorithms do not completely cater to. So we are going to look at a couple more algorithms which take these nuances into control. So before we go to that, types of real-time systems, hard real-time, missing a deadline is unacceptable. So if you miss the deadline, then the whole process becomes meaningless. Soft real-time, occasionally you can miss the deadline. It does not render the process meaningless, but the performance or the efficiency is going to degrade. And firm real-time, missing a deadline makes the result useless or meaningless, but it is not catastrophic. So these are just different types of processes. There are examples given, and I'm sure you can look up or think of many more. So the idea is not all processes are static like we imagined in our examples from the previous segments. So there is a very dynamic aspect to it in terms of deadlines, in terms of periodicity and so on. So the next couple of algorithms we will look at will tell us how we can accommodate that dynamic behavior in our scheduling. So we will look first at this algorithm which we call rate monotonic scheduling. So in rate monotonic scheduling, every task has a period, meaning a period, as in your mathematical functions you have something called periodic functions, right? So there is a period for a function, which is the time interval after which the function starts repeating its behavior. So if you take your sine function or your cos function, their period is 2 pi. So from 0 to 2 pi your sine function has a specific curve, and then from 2 pi to 4 pi it's the same curve repeating itself, again from 4 pi to 6 pi and so on. So at intervals of 2 pi your sine function repeats itself, your cos function repeats itself. Similarly, you have different functions which have different periods, right? So when I say the period of a process, I mean the the duration of time after which the process repeats itself. So if your antivirus lasts 3 months, then the antivirus renewal is going to be a process which has a period of 3 months. within every 3 months that renewal process needs to be performed once. So that is what I mean by period. Every process also has a burst time or a duration, as in the amount of time it requires to be executed. So let me differentiate period and burst time here. Period is the interval within which the process needs to be completed. Burst time is the actual time the process needs to execute. So your antivirus needs to be renewed once every 3 months. The actual renewal will probably take you 1 hour, let's assume. Then 1 hour is the burst time and 3 months is the period. And we will also be looking at something called deadlines in certain cases. So these are the quantities we're going to be dealing with here. So if you look at this diagram here, periods represent the cycles within which the process needs to be finished. T is the time, the burst time required, or the time required for the process to execute. D is the deadline. So within this period, the process needs to be finished by this deadline. So for example, within every 3 month interim, which is the time period, your antivirus renewal, which requires a burst time of 1 hour, needs to be completed by the end of the second month. So that is the deadline. So for every cycle of 3 months, your deadline is the second month. That's an example. So that I hope distinguishes burst time, deadline and period to you. So we'll be looking at these ideas. We'll be assuming each process has one or more of these parameters, and we'll try to come up with scheduling algorithms now.